So we're going to now move on to something totally separate, which is the limit of a function as x approaches infinity or as x approaches negative infinity. What does this mean to say that this is equal to some value L? So this is something that I'm sure you've seen in calculus, the concept of the limit of a function as x approaches infinity or as x approaches negative infinity. The definition of this, however, is totally separate from the epsilon-delta definition that we've seen for x approaching some finite value a. It's like how when we looked at sequences, limits of sequences, the definition for a sequence tending to plus infinity or tending to negative infinity was totally separate to the epsilon definition for it converging to a finite limit. The definition of what these two things mean is actually far simpler than the epsilon-delta definition. It's actually very similar to the definition for the limit of a sequence, the epsilon definition. What we'll see also is that despite the definition of these two being separate from the epsilon-delta definition, the sequence characterization that we've seen for the limit of a function, that's going to carry over and have an analog in the case of these two things. We're just now going to have sequences that either tend to infinity or sequences that tend to negative infinity. So let's use an example to get some intuition for this. So we've taken the example of the function 1 over x, and here is a graphical representation of that function, and we're considering the limit as x approaches infinity of this function. Now hopefully you all know from calculus the answer to this is 0. Let's think a little deeper about why that is. It's because actually the value of this function gets and stays indefinitely close to 0. So however close you want to consider, whatever epsilon you take greater than 0, I will be able to find you a point along the domain. If I go far enough along the real line, I'll be able to find you a point where the value of the function is small enough that it's within that epsilon distance of the limit of 0. And not only does it get that indefinitely close to 0, but it also stays it because, of course, for that point, if you consider anything to the right of it, anything further along, bigger in the real line, closer to infinity, all of those are then going to be within that closeness because the function is monotonically decreasing. It's getting smaller and smaller. So once one point has a value, is being mapped onto a value within that epsilon distance of 0, then all the points after it are being mapped onto something even smaller, so they'll be within that epsilon distance of 0. So yes, it's getting and staying indefinitely close to the limit. So formalizing that then, the meaning of the limit as x approaches infinity of f of x equaling some value L, we're going to define that to mean that for all epsilon greater than 0, so however close you want to be, there must exist some big X within the real line such that if little x is greater than or equal to big X, so for that big X and all the numbers in the real line that are beyond that big X, the distance of the value of the function from the limit must be less than epsilon. Looking at that on a picture, so here is our x-axis, here is our y-axis, and this is now representing our function, and we're imagining that it's getting closer and closer to this value, this dashed line that I've drawn here, which is L, as you get bigger and bigger and bigger. So what this definition is saying is however small you want to consider, we've got our epsilon interval here, L minus epsilon to L plus epsilon. However small you make epsilon, there must exist a point big X. So for each one of the epsilons, you must be able to find a big X. Here is big X, such that if you consider any little x that is bigger than or equal to that big X, so for all this tail end of the real line here, all of their values under the function must be within epsilon distance of L. So if you look at the distance, so if we take, for instance, this point here, look at what it's being mapped onto, it must be inside that epsilon interval, which is what this is actually saying. The distance between its mapped value and the limit is less than epsilon, which is the same as saying it's inside that epsilon interval around L. So that's intuitively saying that the value of the function must get and stay because the entire tail end of the real line is going to be mapped into that closeness, indefinitely close to the value of the limit, because we're saying for all epsilon you must be able to do this, so you can make epsilon indefinitely small, and this must still have a big X that satisfies this. So hopefully you agree that this definition is simpler than the epsilon-delta definition for x approaching some finite value. What I want to highlight to you now is how analogous this definition is to the epsilon definition for the convergence of a sequence of real numbers. And the way we can see this is by thinking about the formalization of a sequence of real numbers. So intuitively it is a string of real numbers like so, but the formalization of that is that it's a mapping from the natural numbers, strictly the natural numbers without zero, because I'm not having a zeroth term, but from the natural numbers to the real line, where each natural number, 1, 2, 3, 4, 5, is being mapped onto its corresponding term. So 1 is mapped onto A1, 2 is being mapped onto A2, 3 is being mapped onto A3, 4 is being mapped onto A4. This function captures the exact same information as this intuitive string of numbers here. So this is the formalization of what a sequence of real numbers is. So we can graphically plot this function also, and this is what I've done here. So here is the x-axis, which is going to be the domain, and here is the y-axis, which is going to be the codomain. And now our domain is just the natural numbers, so we've marked off just the natural numbers here. So this is going to be 1, this is going to be 2, 3, 4, etc. So the function's only going to be defined on those. And then to plot their value that they're being mapped onto, again, we just go up or down the relevant amount so that we're in line with that value, and the codomain is of course the entire real line. So this is at level A1, this is at level A2, this is at level A3, etc. And if it is true that the sequence converges to some limit L, then graphically what that's going to look like is that this graph of points is going to converge up to that value L. So I've drawn the level line for L here. If we then think about the formal definition for this sequence converging to the limit L, the epsilon definition, and think about what it means graphically, we can see that it's utterly analogous to what we've got here. So here is the definition, the epsilon definition. For all epsilon greater than 0, there must exist a big N is an element of the natural numbers such that for all little n is greater than or equal to big N, the distance between the term of the sequence, the little nth term, and the limit must be less than epsilon. Now on the graph, what that means is for all epsilon intervals around L, which I've drawn here, L minus epsilon to L plus epsilon, you must be able to find a big N, which is a natural number, so some point in the domain here, where for that point and all the points beyond it, all little n is greater than or equal to big N, so the tail end of the domain here, they are all going to be mapped by this function, or their corresponding terms in the sequence are all within that epsilon interval, i.e. they're less than epsilon distance away from the limit L. And hopefully you can appreciate how that's completely analogous to what we've done here. All we've done is make the domain more complicated. It's now the real line, but actually the requirement is completely analogous, that you must be able to find a point in the domain such that that point and the entire tail end of the domain is within the epsilon interval, is being mapped into the epsilon interval by the function. Here it's exactly the same. You must find a point in the domain where that point and the tail end of the domain beyond it are all mapped into that epsilon interval. So this is completely analogous to the epsilon definition for the limit of a sequence. So let's move on and we'll quickly look at the definition of the limit of f of x as x approaches negative infinity equaling L. What is this defined to mean? So the definition is almost exactly the same as this, but we need one small modification, and hopefully you can work out for yourself what that modification needs to be. So for all epsilon greater than 0, there must exist a big X as an element of the real numbers. All of that's going to remain the same, but this time it's going to be such that for all little x is less than or equal to big X, because we want the tail end in the negative direction now. Little x is greater than or equal to big X looks at the tail end going this way. We now want to look at the tail end going this way. So for all little x is less than or equal to big X, it must be the case that the distance between f of little x and L, the limit, is less than epsilon. Now let's have a look at an example of this. So I've drawn on the graph here the other side of this graph of 1 over x. And if we consider the limit as x approaches negative infinity of 1 over x, it is of course still equal to 0, because as you get more and more negative, the value of the function gets and stays indefinitely close to 0. So understanding then this definition, for however close we want to be to the limit, there exists some big X as an element of the real line, so some point in the domain, maybe here, such that if you look at the tail end, so all little x that is less than or equal to big X, so the entire tail end beyond that big X in the negative direction, that the value of the function is within the epsilon interval around L, and that must hold true for all epsilon, so it therefore captures the fact that the value of the function must get and stay, that's this bit, indefinitely close to the limit L. Now what I want to look at next is the fact that these definitions for the limit of a function as x approaches infinity or as x approaches negative infinity equaling some value L has an analogue of the sequence characterization that we saw for the epsilon-delta definition for the limit of a function as x approaches some finite value. We'll look at this for the case of x approaching infinity, however, the exact mirror image holds true for x approaching negative infinity. So we're going to see then that if you take a sequence in the domain that tends to infinity, so its limit is infinity, using that separate definition that we've looked at in previous videos in the playlist on real analysis for sequences with infinite limits, then if this is true, it will then imply that the image sequence, so if you take all of these terms of the sequence and map them onto what they are in the codomain and look at that image sequence, that will tend or converge to the limit L. So let's have a look at what I'm claiming on a picture. So we have here now our sequence written out in more detail, x1, x2, x3. On the picture it's looking like this, and we're assuming it is a sequence that tends to infinity, and I've written out to remind you what the definition of a sequence of real numbers tending to infinity is. It means that the terms of the sequence get and stay indefinitely big. So however big you want, so for all big X greater than 0, where big X is a real number, there must exist some big N is an element of the natural numbers, so there must exist a term in this sequence, an X big N, such that for that term and all terms beyond it, so for all little n greater than or equal to big N, those terms are bigger than that X. So they are getting and staying indefinitely big. However big you want, I can find your point where it is that big and it stays forever afterwards that big. And that's true for indefinite bignesses. That's what it means for a sequence to tend to positive infinity. And my claim is that if I take such a sequence in the domain and look at its corresponding image sequence in the codomain, so I look at f of x1, f of x2, and that's kind of shown on this picture as these red dots here, my claim, and I've put a question mark here, is that that will converge to the limit L if this thing is true, that the limit of the function as x approaches infinity is equal to L by this definition. So this is going to be true, and we'll prove it in just a moment, but first note how analogous this is to the epsilon-delta definition theorems about sequences that we saw. It's analogous to that first direction that we proved for the sequence characterization for the epsilon-delta definition. So to prove this then, we need to start with this assumption that the limit as x approaches infinity of the function is equal to L by this definition here. We also need to start with a sequence that does tend to infinity, so we have our sequence here, and we need to then construct our image sequence, and we need to prove that this image sequence has limit L. So we need to prove that for all epsilon greater than 0, there exists a big N as an element of the natural numbers such that for all little n is greater than or equal to big N, those terms of the sequence, f x little n, those terms of the image sequence, are within epsilon distance of L, so the distance between that and L is less than epsilon. So we have to find this big nth term such that that term and all terms beyond it in this image sequence satisfy this property. So given an epsilon greater than 0, we need to show that we can find this big nth term in the image sequence such that they are all inside that epsilon interval around L. Well, this is simple. We just go straight to this definition and then we use this definition. So because of the fact that the limit of the function as x approaches infinity is equal to L, that means that given any epsilon, we can find a big X in the domain such that for that big X and all little x beyond it, so for this entire tail end of the domain, they are mapped by the function into that epsilon interval around L. Now what we do is we apply the fact that this sequence is converging to infinity. We use this definition to say that there will then exist a big nth term in this sequence such that it and all the terms beyond it are then bigger than that big X that we've got from here. So now what we can say is that term and all of those terms are beyond that big X, and therefore if you look at what they're being mapped onto by the function, it must be inside that epsilon interval. Therefore, all of their corresponding terms in the image sequence, so this f of x big N onwards, they must be inside that epsilon interval. Therefore, we can use that big N as our big N here to satisfy the definition for this image sequence converging to limit L. So what we have shown then is that if the limit of the function as x approaches infinity is equal to some value L by this definition, then if you take any sequence in the domain that tends to infinity and you construct its image sequence, then that image sequence will converge to a value, and it will converge to the value of L, the limit of the function as x approaches infinity. So we have proven this direction of the arrow here. However, the backwards direction also holds true, i.e., if it is the case that for all sequences in the domain that tend to infinity, if you construct their image sequence and it converges to the same value every single time, some value L, then you can conclude that the limit of the function as x approaches infinity is L, i.e. this definition and this sequence characterization remain equivalent to one another mathematically. So the sequence characterization carries over to the limit of a function as x approaches infinity in the form of sequences that tend to infinity, or sequences that tend to negative infinity in the case of the limit of a function as x approaches negative infinity. To prove the backwards direction then, we're going to use the same strategy as we did with the epsilon-delta definition. So we need to assume that this is true now. So any sequence in the domain that tends to infinity, if you look at its image sequence, f of xn, it converges to something, and they all converge to the same value, which is L. And we want to prove now that that implies that the limit as x approaches infinity of f of x is equal to L by this definition. And we're going to do that by contradiction. So we will assume that this is not true, and we will derive the fact that this cannot be true, which is a contradiction. So we'll find something that contradicts our initial assumption. So if we're assuming then that this isn't true, we're going to negate this just as we did previously. So if it's not true for all epsilon greater than 0 that this is true, that means there must exist at least one epsilon where it isn't true. We'll call that epsilon epsilon bar. So there must exist an epsilon bar greater than 0 such that the opposite of this is true, i.e. that there doesn't exist an x. So for all big X is an element of the real line, the opposite is true, i.e. that not all the points after them in the tail end of the domain are mapped into the epsilon interval, or the epsilon bar interval around L. So there must therefore exist at least one point in that tail end, one little x is greater than or equal to big X, such that if you look at where it's mapped onto, f of little x, it's not within the epsilon interval, and that should be epsilon bar interval around L. So I've changed that to epsilon bar down here. I've also drawn on the picture what this means, and of course again this isn't going to be consistent with the picture because the picture was representing a case where this was true. But on the picture what this would mean is that if this is now the epsilon bar interval around L, so L minus epsilon bar to L plus epsilon bar, then whatever big X you take in the real line, if you look at the tail end after it of the real line, there must exist at least one little x inside there, such that if you look at what it's mapped onto, and again I've warned you this isn't consistent with the picture, it is outside of that epsilon bar interval around L. That is what this not being true would mean. So we are of course now going to use this to construct a sequence in the domain that tends to infinity, but its image sequence does not converge to L, thus contradicting our initial assumptions. So how are we going to do this? Well, we're going to start by considering big X is equal to 1. So this is true for all x as an element of the real numbers, so it's going to be true for big X is equal to 1. So if we set big X equal to 1, so we can imagine now on this picture this is 1, there must now exist some point, little x, that is bigger than or equal to 1, so in this tail end of the real numbers, such that when you look at what it's being mapped onto, it's outside of that epsilon bar interval around L. we can make that our first term of the sequence, and then if we look at its corresponding term in the image sequence, we know that that is going to be outside of the epsilon bar interval. To get the second term of your sequence, simply double your big X. So make big X now equal to 2, and again, there must now exist a point greater than or equal to big X, such that it's being mapped onto something outside of the epsilon bar interval around L. Take that value and put that as your second term. And of course, it might be the same as this. Of course, this is contained within this, so it might be the case that these two are the same number in the real line. It doesn't matter. Again, when you look at the corresponding term in the image sequence, that is now guaranteed to be outside of the epsilon bar interval. And you then continue on in this manner. So the next one we can double again to big X is equal to 4, and we can find some value that is greater than or equal to 4 such that it is mapped onto something outside of the epsilon bar interval, and we can make that our third term in the sequence. And we continue. We make big X progressively bigger. We double so that it's going to be equal to 2 to the n minus 1, where n is the term of the sequence we are finding. And for every single one of these, we will be able to find a number that is greater than or equal to it, such that when it is mapped by the function, it's mapped outside of the epsilon bar interval. And again, even though the terms of the sequence might remain the same for a while, at some point they must progress because of the way that this big X is getting bigger. At some point it will pass your term, and therefore you'll have to move forward to a new term. So clearly this sequence tends to infinity because it gets and stays indefinitely big because of the way that we are constructing these big X's that are gradually doubling. But of course, the corresponding image sequence is not going to converge to L because every single one of these values is going to be outside of that epsilon bar interval around L, so therefore it cannot get indefinitely close to L. It cannot get within epsilon bar distance of L. So I have therefore managed to construct you a sequence that in the domain tends to infinity, where the image sequence does not converge to L, which contradicts our initial assumption, and therefore it cannot be the case that this is not true, therefore this must be true. So we can now add on the backwards direction onto this arrow. These two things are equivalent to one another. This definition is equivalent to this sequence characterization. This being true implies this being true implies this. And for limit as x approaches negative infinity, the same thing holds true. It's just that you'll be dealing with sequences that tend to negative infinity rather than positive infinity, and the proofs are completely analogous. They're just the mirror image.